So, so in terms of the course schedule, there's homework due Friday that has some questions from chapter 8. Some of it is the material we've looked at previously, one or two sample tests for means and proportions using formulas. For those, you can use the computer to do most of the calculations, but I'd like you to write down the formulas that you're calculating there, so you pay attention to that. There's one problem on a Bootstrap t-test, so it does involve modifying a little bit of code like you did for the last assignment. And I will get your graded assignments back soon. I'll catch up here soon, I believe. And today we're going to talk about the Bootstrap t-test, which really is kind of simulating a test statistic or a standardized test statistic and using that for a t-distribution value and match pairs for proportions, how that's done. I just want to put it in one plug as you're looking for spring classes. There's a number of things within statistics, data science, and so on that are being offered. If you haven't taken a probability class, the 251 probability works well with this one, that it will go into the calculations of means and variances and probabilities and transforming variables and what do their distributions look like. DS202 is one of our data science classes. It's more the computer science side of things and does use Python about managing data and other things with data. And of course there's a whole bunch of math classes, many of which are 217. This I think is 217, right? 07. So scientific computing and calculus 3 and proofs. So a number of these are useful. Some of them are required for statistics, some of them are required for data science, but would be good follow-ups to this or other courses. So within CS, there's also an artificial intelligence course, which could be one elective toward data science, possibly statistics, but definitely data science. And in our department, there's also an introduction to engineering, which is a 2-credit class. So if you're looking for something else and never took that could be an option. So I encourage you to consider those classes as you're considering things. But any questions as we get going? So we want to look at this Bootstrap t-test. And so the motivating example would just be a test for a mean. So if you have x1, x2, right, up to xn. And these things are IID normal with mean mu, the mean mu and variance sigma squared. And again, this IID is this independent and identically distributed random variables. Then this transformation, this pivot, x bar minus mu s over the square root of n, is distributed as a t distribution with n minus 1 degrees of freedom. So this is a t probability distribution. Right, with so-called n minus 1 degrees of freedom. And so then the probabilities would be determined by areas under the t density curve. It's centered at 0 and has a certain shape. Right? And by that, the implications of this curve has mean 0, right? Which even if it's not normal, it still have mean 0. The variance of this particular t distribution. Now for a standard normal, if we could divide by sigma, if we knew that, it would have variance 1. But a t distribution actually has variance n minus 1 over n minus 3, which is bigger than 1 because the numerator is bigger than the denominator. Right? It has skewness of 0. Symmetric. It's symmetric. Right? So there's a few things there. And then the probability in the tails, called the kurtosis, is a little bit heavier in the tails than a normal. Right? So under the, if the data really were a sample from a normal shaped bell curve, and that probability distribution, then this thing would exactly have that distribution. And when we did our testing and got p-values, look like tail areas under here, they would be all accurate. But in reality, sometimes we have small samples, sometimes we have skew data, sometimes we have outliers. So if we bootstrap the data and put the means, it wouldn't necessarily look symmetric like this. It could be slightly skewed, the tails could be a little bit different than this. And so instead of using the theory that we do everything in reference to the t-distribution, we use Bootstrap to simulate a reference distribution, right? Or what are the cutoff values we should use, right? So if n is small and the xi's are non-normal, then our statistic is not exactly distributed as a t(n-1) distribution, and so we're going to simulate and look at how it looks in replications and make decisions based on what we get out of that simulation rather than the theoretical curve. Right? So this is presented as kind of the general case, as a motivating example. If theta equals theta 0 versus an alternative that theta does not equal theta 0. And if our statistic would be an estimate minus theta 0 over the standard error, if what we're going to do, how can we evaluate this statistic here, which has an unknown distribution? So we're going to bootstrap the sample. So we're going to sample n times with replacement, W, from our data. And that's going to give us a new sample, x1 star, x2 star, dot, 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 up to xn star. And we're going to compute our statistics from this bootstrap sample. So from this, we're going to compute theta hat star. We're going to calculate a new standard error, right, whatever that calculation would be. And we're going to get a new t-value. And the way we're going to calculate this new t-value, this is a star here, is we're going to have our theta hat star minus theta hat divided by our standard error. And we're going to do this bootstrap part, many times. Something like 10,000 times, 1,000 times, 10,000 times. So we get all these reference distributions. Right? So it's as if these would be sampled from a t-distribution, but it might be kind of skewed. It might be have a larger tail on one side or the other, and so on. And we're going to use these t stars to evaluate how extreme this thing is. Is this out far or not? If we really had normal data, it would be like simulating an actual t distribution, which we wouldn't need to simulate. We would just use the theoretical curve. And so the tail area, so suppose the t statistic that we got is greater than 0. So our tail area is going to be estimated as a number of t stars that are greater than or equal to our t statistic that we compute above, divided by the number of times we did it. So the t statistic, this is, oops. this is, oh, not again. Okay, touch it. That's, so I'm emphasizing that that's the t statistic that we're calculating from the data. And we're looking at the number of simulated t stars that are greater than or equal to that. And for a two-sided alternative test, then our p-value is going to be twice that tail area. And if the t statistic ended up being less than 0, then we would just calculate the percentage of t stars that are less than going out that way. So whatever's away from the center. Right? And so this should work pretty well. The claim is that this works better than the ordinary t-test procedure when the distribution of the sampling of the statistic does not quite look like a t. When there's deviation, small samples, big outliers, skewness, and things like that. Right? So in the motivating example, when we were doing inference for mu, then our theta hat is just our x bar, and our standard error was s over the square root of n. Right? So then our t value, our statistic, which in the general case is written like this, it is the same as our theta equals mu, theta 0. So if there's this connection, if this is the specific example we're doing, then that what was the general t statistic is the same thing we did with the motivating example. But again, if the distribution skew, small sample sizes, it might not be exactly normal. So that's the idea, right? We can simulate this, and you're going to do it in this one sample case, you can do it in two sample cases, and you could actually apply it to a whole variety of statistics that you might not know the exact distribution. Right? If we had chosen, trimmed means or the means with the latest, taking out the, shrinking the largest and smallest values toward the center a little bit, so it's kind of an unusual thing. We wouldn't exactly know the sampling distribution, but we could still simulate it. Right? We could still do a test. So let's look at an example today, right, of doing that. So there's a bunch of data in R that comes with it. And here's the names of a bunch of data sets. For any of these data sets, you can type help of that data object, and it will tell you about it. There's one called chick weights. This is the data set. The grams that the chicks grow after about 6 weeks, and the type of feed they have. Right, help of chick weights. An experiment was conducted to measure and compare the effectiveness of various feed supplements and the growth rate of chickens. Obviously, big business application, right? So, the weight in grams and the feed type appeared in Biometrica 1948 under Anonymous. It was published there for some reason. There's a few little bit of data there, but I'm going to attach it. These are the number of chicks that were raised on the different types of material. Casein is one we'll look at here. Casein is a primary protein in milk. Right? But before we do that, right, so these are Foxplot. There's this little command, LAS equals 3. So it's the orientation of the axes. Let's see if I run that, does it work? You can see it a little bit better. Right? So sunflower, soybeans, meat meal, casein is up here, this one. Right? And so we could look, we're going to make up an example using just the one sample of casein. Right? Does the casein values, do they look normally distributed or not? Right? Casein is a protein in milk. So you could look up any of those other feeds and find out what they constitute if you're interested. Right? Well, I'm going to assign the weight based on the casein chickens to that. Here's a histogram of casein. It's only 12 observations, so it doesn't end up being too normalish. It's a little bit skewed to one side back in the plot. This is the first quartile. That's the third quartile. It looks a little bit skewed. The minimum value looks a little bit farther away from that. So it's 12 observations, a little bit skewed. It can't be. You probably couldn't distinguish it from normal in a test because there's such a small sample size, and it's not that bad, but it's still a little bit non-normal, right? And so let's ask the question: is the average weight 300 grams? I just kind of made that up as an interest. Kind of looked here. Is 300? Would we reject it? It's pretty close. There certainly are values below it, but is there enough evidence that the average is higher? If we do a t-test, we could do that, right? We would get a t-value of 1.2679, and so a p-value based on a two-sample t-test of 0.231. Right? So we can't reject 300. Right? There's not enough evidence that 300 is wrong. You see how this goes. 300, the mean is put in there. Arguments, t-dot test. It doesn't tell you there exactly how to do it, but if you do help of t-test, then you see mu, you can get different values of mu. If you just do a t-test and don't put in a mu, it's going to assume you're trying to test it versus 0. And these are weights of chicks, so 0's irrelevant. So that's, if you did a confidence interval, right, you would get 282 up to 364 grams for the weights. The estimate of the mean was 323, so it's kind of in the middle here, right? How's that interval calculated? Well, it's calculated with the t-values, right? 12 chicks, so 11 degrees of freedom, standard deviation divided by the square root of 12, and you get that interval. How is this t-statistics calculated? Well, the mean minus 300 divided by a standard error, and you get this 1.267. Under the model, this p-value 0.231, right, gets compared to a t-distribution. Right? The probability that you're less than that under a t, well, 1 minus that is the probability you're bigger, and so 2 times that is double the tail area, right? So that's where that p-value came from. But it relies on the exact shape of the t-distribution. 2.2 would be the 95% critical value. So we would reject if the t-statistic is beyond 2.2. But it's 1.2, so it's not that far out. That's all well and fine. Oops. Thank you. Right, so if we wanted to bootstrap this, right, so then I look at this. You could look at any of these plots. The stem and leaf is fine for this one. It kind of mimics that histogram turn on the side for the small one. Is it normal? That's a little curvy. 12 points is not all that much. Or a box plot by itself, a little asymmetric. To do the bootstrap t, we set up a vector to hold all our t stars. Right? I call it what you like, t star or something else. And then we loop through many times, and we're going to sample casein with replacement. Right? And then compute this. Right? S is the sample values. So the mean of the sample values minus the mean of casein, divided by the standard deviation of our new sample, and it's still square root of 12. Right? So that should give us new t-statistics. And honestly, I need to think a little bit about, not every book does this or presents it, and I don't know that bootstrap t is the most, it certainly makes some sense, right? But it's a little bit newer. I mean, it's been around since the 70s or 80s when they described this, but it's not so much in introductory books. It's not necessarily so, the default method in mathematical statistical books, many of them. So it's kind of certainly in my lifetime and probably within yours, kind of more advanced bootstrapping things are kind of entering the mainstream. So that's why there's books like this that include it. So I know I have to think more about what this means in all cases to put I know we're doing the approximation of the population by the sample. So where we're used to have a population value, then you put in the sample value. So anyway, but I'm still thinking, do we want the mean here or the theta 0 value. But anyway, this is what the book says consistently in a couple places. So, but following that, we do run our little sample, and how many of the bootstrap values are greater than 1.26789 point? That's the t-value, the t-statistic that we computed before. And 2 times that, it was like 2712. I didn't have any number seed that I set, so it's slightly different variations, but it's still about 0.27. What was it for the other one? Had a t-value of 0.23. So it's a little bit different, but it's comparable in terms of its message, right? That there's not a significant difference from 300. If you want to make confidence intervals, right, you could do a confidence interval. We have a t-statistic, the t intervals. We would use cutoff values, so it's minus, and so you put the bigger one here and the smaller one here, because there was that pivot reversal thing that happened, and you get this confidence interval. And that one's comparable, right, to the one from the t-test procedures, but it's a little bit shifted lower. So it's shifted over 5 units, 5 grams, reflecting the non, we could actually look at those t-values. What do these values look like? Here's the bootstrap of the t. And you kind of get implied by that there's kind of a bigger tail out here, right? The slight non-normality of the distribution of the weights of the case set means this is a little bit normal. And if you do a QQ plot, it kind of gets that line. Now it's not really normal, right? It's a t, so you would expect a little bit of that, but maybe this is a little bit more. And it's a little more pronounced on one side than the other, so that's skewness. Right? So anyway, so that's the concept, right? Simulating the t-distribution instead of just using the theory and making it match better to the small sample reality. You can do it with 2 samples too. But any questions on the 1 sample one? What was the general procedure that we had? So we have our t-statistic. We calculated that with the real sample, and that based on the null hypothesis of 300. We bootstrapped and got these t-stars, right? And then we looked at tail areas and the p-value. It was kind of similar, and it was a big p-value, like 0.27, right? So it was not unusual. 1/4 of the time, getting something at least its extreme does not seem like a surprise. And so we do not reject the null hypothesis. So it could be 300. If you saw that same graph, that same box plot, but it was based on 12,000 chickens or something, then I'm sure you would have rejected, right? Because the standard error would be so small that any size of difference almost would get rejected, right? Okay, so we can do this with other settings too. We can do it with 2 samples. So we're going to compare it to soybeans. So if we go back a few plots, where are they? Right. Casein and soybean, these 2, right? On that plot. You can do a box plot where you get those two things there. So casein and soybean, these kind of look different, right? But it's kind of a small sample size. This one's a little bit skewed, this one's a little bit skewed, kind of in the same way. Right? But maybe not as much. Neither of these samples are really too bad. I don't think most people would object strongly if you gave the t-test results, but we can see it's a little bit different. The t-test results here give us a t-value of 3.27. That p-value is 0.0035, so that is significantly different. So this is significantly higher. We judge that because the p-value is small. You can report a confidence interval, right, for the difference here. 28 up to 126, it's all above 0, so the casein is higher, and it gives the 2 means there. If you make variances equal in these 2 kind of similar spreads, right, you could look at the standard deviation of casein, standard deviation of soybean, right? 64 versus 54 doesn't seem like too much. You could, to me, that would be plausible to use this thing where they're true. But again, you get a t-value that's pretty big and a p-value that's kind of similar to the other one, 0.0035, 0.0029. Again, quite small. These are not the same. confidence interval is a little narrower, 28 to 126, and this is 29 to 125. So it's a little narrower. Having that common variance seems to help you. There's a couple ways to do this with simulation. Right? One was the permutation test that we did early on. Right? So in this case, we have the two groups, and they're assigned this way to these two groups. But if there's really no difference, it's like we pooled one sample from a population and called it casein. We pulled another sample from that same population and we called it soybean, but really there's no difference. Right? So 10,000 times we could sample. So this is going to combine the casein and soybean data together. This gives me a nice list of 26 values. There are 12 casein and 14 of soybean. And so I'm going to sample some indices here. This is the part, sampling indices, right? So I'm sampling from the numbers 1 through 26 and calling that the indices for sample 1, right? And then I'm going to create the sample 2, which is the indices 1 through 26, taking out the ones that I did before. Right? So minus S1 means I'm taking out the numbers, whatever those row numbers are. There'd be a couple ways of doing this. But I get S1 and S2. Now I do dat of S1 because I sampled indices. I haven't sampled data values, right? And then dat of S2. I wouldn't really need this second line here. I could have just put negative S1 there, and it would have taken my data and taken out those certain row numbers. It's kind of an extra line, but kind of illustrate working with indices. So, and then so take the average difference, and that's my permutation. Right? So then I can compare my permuted average differences with what I actually did in my data. So how does that look like? That's the histogram of differences. My actual one, casein minus soybean, is there. Right? So it's not the biggest, but it almost is. Right? And so then my p-value is what percent are up here, and I multiply that by 2 if it's a two-sided test. 0.0034. So that's pretty small. What was the other one up here? When it was equal variance is 0.0029. It's pretty similar to that, right? So one little detail that I noticed in the book is that this permutation really makes the most sense when the variances are equal, right? Because you're putting all the data together as if it's one population, and then you're testing about the means, right? If one had greatly a lot more variance than the other one, it wouldn't really make sense to do that, right? It'd be kind of two factors, both the mean and the variance. So anyway, this permutation, if they're equal, variance makes the most sense. Bootstrap T, it doesn't matter, because the bootstrap T, I'm going to call it bootstrap boot.2T, so the bootstrap T test with two samples. Right? So we set that up. We're going to sample 12 with the cases with replacement. This one, we're going to sample the soybeans with replacement. And this one is sampling the actual values of casein, like I did initially, right? No indices there. The indices were easier to use in a little way, because I needed to actually split it. It had to be without replacement, and then split it into two. So whatever I took out the first time, I had to take it out the second time. And so that's a little bit harder to, you kind of use the indices for bookkeeping to keep track of where things are going. So I don't know, that's how I think about it. So you can do these values directly. And so the mean of these two groups, I'm going to get that a little bit bigger to see what it is. You can see it on the page there. But it's the difference in the means here minus the means of the casein and soybeans. Now when we do the t-test, we use 0 there. But the book says use the data to determine wherever it is to get the simulation. So that's what we're going to do. And then the variance of the new samples divided by their sample sizes. And these can be unequal variances. So that's would be the t-test. Here is a histogram of what those t-values look like. Is it kind of normalish? It's closer, again, but it's t, so you expect a little bit wider tails. But p-value then is our t-statistic from unequal samples is 3.274. So if you look back up, right? 3.2743. Wow, it seems to have highlighted that for me. That's kind of, I didn't expect. I highlighted that. So maybe I copied that, or I don't know, that's kind of freaks me out that doing that, but anyway. But it's greater than that. So how many times does that actually happen? If you highlight that part, you can run that. So 36 times out of 10,000. Right, so twice that is 72 out of 2,000. So this one is 0.70072. When I did it originally, it was 0.0074, but that's pretty close, right? This is larger than the other p-values, right? Possibly accounting for a little bit of skewness and things like that, but it's still awfully small, right? So these things are not equal, right? So if you want that higher yield in terms of weight of chickens, then the casein supplement seems to be superior to soybean, right? If you're an economist, you would think about cost of these inputs and cost of the extra, what value of the extra weight and so on. But any questions about it? So the book discusses, right? And a couple of the problems says, which interval should you report? Which interval or test procedure? Report. Right. And right, so let's think about the two means case. In this case, we had the t-test, two-sample t-test, Welch, or there's the Welch version with unequal variances. There's the equal variance version. There's a permutation test. And then there's a bootstrap T approach. So there's really kind of four ways of handling that. Right? There should be a consistency between reporting confidence intervals or p-values, right? So that if it's in the interval, it's not rejected. But if it's outside the interval, outside of what you're testing about, then it should be rejected. So that those should be, right? The permutation test is the one that they like the best if variances are equal. This is the one they like best if there's unequal variances. They also like it as second best for equal variances. And so it would put these things as third, or second, second or third. Right? And given the logic of how many analyses go, if possible, using the equal variance has some advantages. If you go on to analysis of variance and have multiple groups, there's an equal variance assumption built into that. But if you go on to regression, there's often an equal variance assumption built into that. So abandoning equal variances, then continuing with analyses where you're comparing means, it's a little harder to see where that assumption lies, but it's still there. So if the equal variance looks reasonable, then there's something that I think is good about doing that. But that said, if they are pretty unequal, then assessments of significance, either for Bootstrap or the Welch, can go. So there's some discussion about that, and I think that there's probably debate about if you move on to other procedures about what exactly should you do. But how are they making these judgments? Right? What are they thinking about with that? Right? And any of these things can be viewed as procedures. You give me the data, and I'm going to do these calculations and report a p-value and then interpret it. And they all have their ways of doing that. And that's essentially any data set that comes in, it processes it and gives you a result. Right? The key idea, right, is some type of accuracy. Right? If H0 is true, right, the chance of rejecting H0 should be small, right, if our statistical significance is 5%. Given by alpha, right, then we want to reject true H0s less than or equal to 5% of the time. I know that's not a complete best sentence, right? So that if the nits and the null hypotheses are true, you don't want to reject it more than 5% of the time. And so that the ones you do reject stand out. Right? If you were rejecting the null hypothesis 10% of the time or something like that when they're true, you're making too many errors that way. Right? You only want to reject typically when there really is a difference. And so you don't want to reject the ones that aren't there. And so they look at across different scenarios, when do you reject what percentage? And the claim by the authors is the two sample t-test or the bootstrap t-test ones get closer to that 5% around number of scenarios where variances are unequal or there's skewness or there's outliers, and it seems to adapt to the particular data set rather than try to follow a theoretical curve. That said, in most cases, there's not a whole lot of difference, right? And samples have to be pretty small, or things have to be pretty skewed for things to really kind of break down substantially. But you can reinforce a conclusion by showing how it's rejected in multiple ways. Right? So if you did the ordinary t-test with equal or unequal variances and they both get the same conclusion, then there's less question about that assumption. Right? Or if you do the bootstrap t and a t-test and they get the same conclusion, then you're not so worried about the assumptions of the statistical method giving you a result that's not right. If they come up with slightly different things, you're probably at the borderline anyway, and there's a little bit more to try to investigate and explain. So you could learn something even if the tests give you slightly different results. Right. Yes?
So is the big difference that t-tests assume that your data is normally distributed?
Yeah, so the derivation that originally gave to the data, the statistic coming from a t-distribution, the only way to derive it is starting with the normal. And so if your histogram of the data looks reasonably normal, not too severe, or kind of bigger sample sizes. Like if we had, instead of 60 chickens, we had 600 chickens, about 100 per treatment. Then even if it were kind of skew and there was a few extremely large ones or extremely small ones, then it wouldn't. It could be a situation that some of the chickens die, or they transfer some chickens from a different batch into there. Things get mixed up, kind of. And so you could get some ones that are 4 weeks old instead of 6 weeks old, and so then their weights are off. And if you got a few of those in there, they would stand out as outliers. But if you have 100 chickens and a couple of outliers, it's not going to affect the shape of the distribution as much. Right? The other thing that happens if skewness is extreme is consider a transformation. So if your data y is really extreme and it would kind of look like this, a huge massive tail and some values that are way out there, so this is y, then taking something like the log of y or square root of y changes the problem, and the meaning of the mean is different. One's on the regular scale, one's on the log scale. But if you're comparing two groups, it might be reasonable to compare them on the log scale. Right? And so before you get into a situation with extremely skewed data, it's good to look at it and think about, is there a measurement error that caused a few extreme values? And if it's generally extreme, is this all the homogeneous population that you want to study? You know, maybe there's some individuals that would fall into one category and other individuals that fall into another category. And if most of those that are really extreme are in that second category, you can kind of isolate them or say they're not part of the study. It does limit what you can conclude because you're limited to your where you're getting your data, but it might deal with some of that problem, right? So often that's done and important for practice to look at the type of data, right? What it looks like. That's the main idea of the bootstrap critique. And in practice, you want to look at the data, maybe transform and deal with extremes one way or the other. Sometimes these extremes are related to size. So maybe you can take a ratio. Instead of number of cases of something, I'll write that down as another possibility. Ratio, you know, y divided by some measurement of size. So the number of motor vehicle accidents per 100,000 people, right, might be less skewed than just number of motor vehicle accidents. Right? If counties range in size from a few thousand people to another county that has nearly 1 million, and there are counties with 1 million people in them, right, then their number of accidents is going to be hugely skewed. But on a per person basis, or, you know, per 100 people, per 1,000 people, those ratios might be less skewed. It might be easier to interpret in some ways, right, without that effect of size in there. So, right. Okay. So another topic to go back and pick up a piece, matched pairs for proportions. Right. Now we've done matched pairs for, you know, quantitative data. Right? If you had dollar sales at one time period and dollar sales the next month for a series of stores, and at the same stores, you take the difference, right? The difference, and you're back to essentially one sample. But the matched pairs for, this is an 8.3.3, two, so we have pairs of data. And we have success, failure for both. And the pairs have correlated outcomes. Not independent samples. Right. So how do you get this? If you have a group of students, for example, pre-test and post-test, right? And you record whether the score is greater than or equal to 70, right? And you have a bunch of students doing this. Right? If the same students, you know, take the pre-test, post-test, you record passing grade or not for each time. One example in some of the books, you're evaluating a sunscreen, right? You have two different sunscreens. You have treatment A, treatment B, right? And then each person takes, you know, a coin and flips it, and if they get a head, they put the sunscreen A on one arm. And if they get a tail, they put sunscreen on the other arm. And they put the other brand on the other one. So both people, every person has both of them on. It's kind of a randomization across the arms, and so then you do a measure of reaction to the sun, right? And so they get some people are lighter, some people are darker, some people get more exposure, some people less, but it's more or less constant for that person across their arms. Not exactly, because people tend to do things with one arm versus the other, so you get a little differential exposure there. But the difference, and then is it burnt or not? Right? Do they get burned or not? Is it severe or not severe? And so each person would get 2 ratings on the A and B, and they're correlated. Right? People very light, who get a lot of exposure, probably get more burnt on both, right? And vice versa. So you can do other things, like you could have another example where something like this could happen. So say you're doing a study in education, and you're looking at the attendance impact of a free breakfast program. There's some school districts where the majority of children, or almost 90% of the children, would qualify by poverty standards for free or reduced price meals. Right? And in some of those districts, instead of having the children have to log in and say, I get a free one, which is an indication that they don't have much money, they just give everybody free food. Right? And some of them even give free breakfast. So for some children in the public schools, 2 meals of their day are coming from that program. So if you add a free breakfast program to a school, you improve attendance. In some of these poor areas, attendance is all horrible, right? Down to like 50% some days. And just kids are getting through high school somehow, but they're not there. So they don't have a chance of succeeding. So you could think about a treatment where you school, so the units are the schools, right? Each school is either going to add a program or not. School adds free breakfast for all the kids who show up. Of course, they might sleep in and not come for it, but and the alternative is the school does not change, right? So you could randomize and say these group of schools get free breakfast, or pick some of them, and then look at other schools that don't have it, and then compare attendance. What percent of the students are there on certain days, or certain 20 days out of 25, or something like that, right? But there's a lot of noise in this. There's a lot of differences between the schools. If you let schools pick to add a free breakfast program and pay for it, well, some are going to pay for it and some aren't. So there's going to be a bias. There's going to be confounding. You could randomize, but if you just do complete randomization, you could have, there's still, you're not probably, maybe at 30 schools total. You're not going to do this for 1,000 schools. And so you have 30 schools possible, and 15 get free breakfast. You could still end up with something that's kind of imbalanced, right? You could have the schools that are a little bit more financially able, or a little bit more stable communities getting it just by chance, and then the ones that are less stable and have bigger attendance issues not getting it. So it's a little imbalanced because of a small randomization. Right? How could you stabilize it? Right? You could use matched pairs. Right? You could take your schools and measure attendance or something, parents' social economic status or unemployment in the local area, and take the 2 schools that are at the worst, right? And randomize, and one of them gets it and one doesn't, right? And then go to the next pair, right, and randomize them. And then at the top, you have of this 30, you have the ones that are doing the best, and one of them gets it and one doesn't, right? So that across whatever these factors are, you at least controlled it a little bit, right? So you end up with matched pairs, right? So the schools are on this side, and half of them get, matched pairs. So even in big studies like that, and this has the free breakfast, and no change. Right? It's not that you're taking away something that they're already doing. That probably wouldn't really go over so well. Right? But if you can add free breakfast to some of them, then in the resources you have, and you can't do everybody, then you might learn something, and that would benefit everybody potentially in the long run. So, but it's matched pairs. So the data that you're going to get, right? Then you can make a 2x2 table, and let's see, what did I do for notation? There's the first time and the second time, or the first one in the pair, the second one pair, and are you successful or not? Kind of a yes or no response, or a yes or no response, and you're going to get like that. There's n pairs in all, and say that these are the counts of the numbers that are in there, you could estimate the probability that you're going to get a yes in the first group, the first type of school, the pretest. What's the chance of passing? The way you would estimate that, well, is you're going to aggregate over here, right? And you're going to get A plus B over our sample size to estimate the proportion of yeses the first one. Now you have the post-test. What percent pass on the post-test? The p-hat of yes 2 on this one is A plus C, right? So you have A plus C, right, over N. You can estimate most of those proportions, but if you take the difference of them to compare the rates, they both have that A in there, and so they're related to one another. Right? If one's high, the other one's likely to be high too, so they're correlated. Right? So these two things are correlated, and it's because the likely response of the members of each pair are similar, more similar than random. Right? But if the proportions are the same, right, then the random split into B and C can be thought of as a flip of a coin. 50-50, if you don't match, you end up in B, and 50-50, you end up in C, right? So if P1 equals P2, then placement of non-matching pairs, where one has a yes, one has a no, or vice versa, pairs into the counts B and C. It's just simply random. So testing this with these correlated proportions, we actually redefine things. We're going to ignore the places where they do the same, right? So we're going to let N, right? We're going to let N prime, the number of non-matching pairs is what we're going to deal with. And we're going to have a hypothesis that the proportion split between B and C is 50-50, which is an assumption that there's a proportion dividing those that's just 1/2. This is an alternative, that the proportion dividing between B and C is not 1/2. Right? And our estimate of this p-hat, the split, is going to be the number in one of the categories over the total, or B over this new N prime. Right? And so we've reduced this issue about testing these correlated portions really into a single proportion, but not about the full sample, but about the sample where there's disagreement. Right? Discrepancy. And if it's p equals 1/2, depending on the sample size, we might calculate the exact binomial probabilities, or we might use mean normal. So let's look at a quick example with that, right? So, let's say you take 300 registered voters and contact them on 2 different occasions. Let's say you contact them in September, you contact them in October, the same people, and just because political things are in the air, do they approve of the job that President Trump is doing, right? And there's approve and disapprove, and approve and disapprove. There's 300 pairs in all, and let's say, based on the polls, it's about 40% or so. But let's say it was 45% here. So that would imply that you'd get 135 out of the 300 saying approve. Right, so A is approve. B is disapprove. Some people probably respond that they don't know or don't want to tell you, but in any case. And then let's say that in this case it's dropped, right? There's all this fair, the impeachment hearings and all that, right? So that would be dropping to 35%. Right? And these are the margins, but they're correlated proportions. So people would answer. So let's say that 95 people approve both times, and 155 disapprove both times. These things have to add up. So this would have to be 40, and this would have to be 155 actually, and there'd be 10 here. So we'd end up with this split. Right?
So we ignore the ones who haven't changed.
Yeah, to do this test, we're going to ignore the ones that haven't changed, right? And our new sample size for testing is going to be the 40 plus 10, or 50, right? And the null hypothesis is equal proportions, right? And so, oh, that's an N. Made it look, right, so that's, oops, go back, there we go, right? Our estimate that we're going to compare this to is, let's take the bigger one, 40 out of 50, right, 0.8. Right, so this is 0.5 versus 0.8. They look pretty different. To evaluate this statistic, you could use a normal method. Our z is going to be our 0.8 minus the null hypothesis of 0.5. 0.5 and 1 minus 0.5 for n. And now we'll use the 40 there. So we'll get that z value. And what does that come up to be? So it's 0.3 is the difference. And then we need a square root of 0.5 and 0.5 over 40. 3.79. So the z value is 3.79. And so the probability a normal is bigger than 3.79 is about 0. Right? So this is going to get us a p-value that's very small. Right? You could say it's less than 0.001. So using the normals, you could do that. You might make a continuity correction. It's not going to change the things too much. It's still going to be pretty extreme. The other way this could be done is add up what's the probability that a binomial is greater than or equal to 40 when we have 50 trials and a probability of 0.8. That'd be one-sided, and you can probably multiply that by 2 to get a p-value. So you could calculate a binomial size. What's that? Density for a binomial going from 40 to 50 out of 50 trials, and the probability is 1/2. Those are all those different probabilities.
All of the probability was 0.8.
So, but we do the testing under the null hypothesis of 1/2
Okay.
of an equal split. Right. And so that's partly why we use the 1/2 as the mean here and 1/2 as the proportion here. But under the null hypothesis, that's what it would be. Right. And same thing here. 0.8. That's where.
That's what the confusion.
That's the confusion. The sample proportion is 0.8. We test under the null hypothesis. Thank you. So there's this density for those are the individual probabilities. If we add those up, right, we get a small number, and multiply that by 2, it's still a small number. So this number means 0.1, 2, 3, 4, and then 2, 3, 8, and 6. Right? So it's quite small. The p norm, 3.79 number, is also a small number. And so that means that there's a significant difference between those. So if you change things, if this was 135, 165, and this was 135, 165, and you had 90, so if it was closer, right, there'd be less of a discrepancy here, and it might not be significant, right? But this generally comes under the name of McNemar's test. Test for correlated proportions. So if you Google that, you should find an example or description of that. Did I put anything else? No, I didn't put anything else. So you might be able to find the McNemar's test. Wikipedia. Paired nominal data. So it looks very much like what we did there. This is as a chi-square. That's a square of the normal, actually. So it's where you can do the binomial exact calculation there. And there's an example, a couple examples, and it appeared in Psychometrica, which would be, I think, the premier journal in psychological statistics. And you could find it through JSTOR. I guess that should be available online if you wanted to look at that. Anyway, so it's possible to do a bootstrap type test for this. We don't really kind of have time to go through it all. I'm not sure if it would really be done in practice. So if you think about the data set, we have n rows of ones and zeros. How would you bootstrap that data? It's pairs, so you can't bootstrap one variable at a time. But you can bootstrap the indices. If you bootstrap the indices, you get a new set of paired data. And then you can calculate the sample. You can make a new table, get the A, the B, and C off diagonals, and get any statistics you want, right, based on that bootstrap, and then compare that. I don't think you really need to do that in this case, but in principle, you could use simulation in the same way to look at the problem. But this one with binary and doesn't seem to have the same issues as the t-distribution one with skewness. So, but anyway, great. On Wednesday, we'll look at 8.4 on mean hypothesis test, and the homework is posted, and oh, good, thanks.
Thank you. Thank you.
You're welcome. Have a good day.